Hey physics fans, it's Major Rayhan and I'm going to talk to you today about vector addition. If you're looking for a video about how to add vectors with x and y components, that'll be the video after this one. I'm just going to talk about the geometric constructions for adding them today. Alright, so vectors are important when we're talking about several key fundamental quantities in physics. And a vector has a magnitude and a direction. Another way of saying that is a quantity which can be completely described by reporting a number of units, that's a magnitude, and its direction is a vector quantity. Now if you just give one or the other, that vector quantity is incomplete, it doesn't make sense. So in order to communicate clearly and solve problems correctly, when we're talking about vectors, we need that magnitude and direction. Vector notation is accomplished in your book by bolding the letter and putting a vector hat over it. When we're using handwriting, we'll just put a vector hat over it. Similarly, the magnitude is just that quantity without the hat on it. Now, adding vectors, we can add vectors, we could subtract them, or we can multiply them. We can't divide vectors, that quantity is undefined. Adding vectors in one dimension is pretty straightforward. Here I have A and B, and they're along the same line. Their magnitudes are both the same, they're both 5 meters long. However, A is in one direction, B is in the other direction. And it helps us to write a coordinate axis system in here to be able to talk about their directions. We can see B is in the positive x direction, and A is in the negative x direction. These two vectors, because they're on the same line but pointed opposite from each other, we can call them anti-parallel. If B was reversed and pointing in the same direction as A, they'd be parallel vectors. Now, A is not equal to B because their directions are opposite each other. However, the magnitude of A is equal to the magnitude of B. If we want to add them, we keep track of what direction they're pointed. So B is in the positive x direction, we'll call it positive 5. A is in the negative x direction, we'll call it negative 5. And so if I do A plus B, it's going to be 0. That's one-dimensional vector addition. Two-dimensional becomes a little bit more complicated. So here I have two arbitrarily placed vectors, A and B. They're coplanar. It means that they are in different directions, maybe the same direction, but they're in the same two-dimensional plane. A is some angle phi above the horizontal, and B is some angle theta above the horizontal. Now there's two ways I will teach you how to do a geometric construction for adding vectors two-dimensionally. Oops. The first way is the parallelogram rule. So I'm going to redraw A and B. Here's A. Here's B. And what I've done is I've translated them. So remember, we can always translate a vector, and that means to pick it up off the page and move it somewhere as long as we don't change the magnitude and we don't change the orientation to some point. And so here we could still see that A is angle phi above the horizontal and B is angle theta above the horizontal. However, they have a common origin. Now when we're doing the parallelogram rule, we'll just inscribe a parallelogram here by extending both of the ends of those vectors out until they meet, and drawing a third vector, or the resultant vector, from the origin to the end of that parallelogram. We'll call that R. It's important to note that while R is the sum of A plus B, R is definitely not the sum of the magnitudes of A plus B. That's probably one of the biggest mistakes that we see in physics, is folks just try and add A and B to come up with their resultant, without giving any heed to the fact that they have angles here. All right, the other way I'd like to teach you about adding two-dimensional vectors is the tip-to-tail method. We can think of this as tail-to-tail. Tip-to-tail works if we have more than two vectors, but it also works great if we only have two vectors. So again, I want to add A and B. I'll redraw A here, making sure to translate it correctly so that its magnitude is the same and its horizontal orientation is the same, its direction. Then I'll do B, and I'll put B's tail right at the tip of A. Same thing here, I've translated it correctly. Same magnitude, same horizontal orientation. Now if I draw R back in here, we see that the resultant vector R is the same in both cases. It has the same magnitude and the same angle above the horizontal. So, for a review on how to add vectors by their x and y components, check out the next video.